Welcome. In this video, we're going to take a look at the idea of the index of hydrogen deficiency and also touch on IR or infrared spectroscopy. So the IHD, index of hydrogen deficiency, is also referred to as the degree of unsaturation and provides clues about the structure of a molecule once the molecular formula is known, because if you can add more hydrogen to a structure, it means it's got some double bonds or a cyclic structure. So unsaturated just means you could break open some bonds or break open a ring and add more hydrogen in as single bonds to that. So for example, C2H4 is an unsaturated hydrocarbon because it has a double bond between the two carbons and then two hydrogens on each carbon. And so to saturate it, I would break the second bond, the pi bond on the double bond, and I would add a hydrogen here, and I would add a hydrogen here for a total of one H2 molecule, so its IHD would be 1. So to determine the IHD, a couple techniques you can use. I tend to sketch the molecule and then either go ahead and saturate it and count up the hydrogens I put in, and then you divide by 2 because it's really hydrogen molecules. So either think of it as the hydrogen you needed or the H2 you needed. Or just look at the sketch, and any double bond can break apart and take a hydrogen molecule, one on each side of the broken bond, or a ring structure can be broken open and will have 2 open ends, which will use 1 hydrogen molecule. Or a triple bond will have 4 open spots. So basically you can just go through and count. Each double bond gives you 1 toward your IHD, a ring structure gives you 1, and triple bond also gives you 2 to count toward your total. Otherwise, you can always use a formula. If you have the molecular formula, such as CXHY, then you can use the formula 2x plus 2 minus y divided by 2. But I find it more work to remember the formula or figure out the formula than to just go ahead and sketch the diagram I'm interested in. So if I look at my 2 examples here, I've got C4H9N. So I'm going to draw 4 carbons in a row and attach a nitrogen, and I'm going to assume single bonds throughout, and I'm going to start adding hydrogen until I run out, and then add the necessary multiple bonds if there's any necessary. But with this structure, I would need 3 carbons or 3 hydrogens to saturate this carbon. I'd need 2 here. I'd need 2 here, and now I'm up to 7. So if I put my last 2 on the carbon, nitrogen would be left without its last 2 bonds. So this indicates to me, I could actually just go ahead and fill it up, and that would give me H11, which is 2 more than I have room for, which indicates I need a multiple bond, or indicates that my degree of saturation is 1 hydrogen molecule, or 1. Now with benzene, I can go ahead and draw the structure, and benzene has a cyclic structure, and it's got the alternating double bonds. So each of those double bonds could break open and take a hydrogen, which would be 3, but then the ring itself could be broken open to make this a straight chain isomer, which would be another 1. So benzene has an IHD of 4. IR spectroscopy is one type of electromagnetic spectroscopy. Just means you can use any electromagnetic wave to try and get some information about the bonds or the structure, something about the molecule. And we use radio, microwave, infrared, visible, and ultraviolet light all to do these things. And each type produces different information. For example, radio waves are used in NMR, which we'll also talk about. But infrared is used in IR spectroscopy, hence the name. So kind of the big picture is that infrared spectroscopy focuses on the vibrational energy of a bond. And if you have a polar bond, the vibrational energy being given off is going to fall into the IR region. And it's going to be different for any 2 elements bonded, or if you have carbon and oxygen single bonded versus double bonded, that will have a different frequency. So a molecule with more than 1 bond type will have a spectra filled with some peaks and troughs, and the troughs are used to identify the exact bond that we feel it is. You can also use these troughs to identify the quantity or the amount, like we do with the breathalyzer. We're looking for the OH or the alcohol bonds in ethanol, and we're looking for how much. So you have a chart like this in your data booklet, and it shows the wave number associated with specific bonds. Now, it certainly doesn't have all bonds on here, but it has many. It has the 4 halogens bonded to single bonded to carbon. You have carbon and oxygen single bonded, like you find it in an alcohol, an ester, and an ether. It has the C double bond, carbon-carbon double bond, like in an alkene. A carbon-oxygen double bond, like in an aldehyde, ketone, or carboxylic acid, along with an ester. And then the carbon-carbon triple bond, like in an alkene. It's got 2 different OH hydrogen bonding frequencies, one for carboxylic acids and a different one for alcohols. And then the CH is roughly the same range for alkane, alkene, and arenes. And then finally the NH in amines. So you notice each one is given a range. Since the wave number will be altered by the bond environment it's in, what other bonds, what other atoms are in this molecule that might be affecting the band length. So we see a range given for each one. Also, it often gives a description of the intensity that you can expect the bond to look like. If it should be a strong intensity, a medium or weak with multiple bonds, you can see there's different descriptors there that are also used in IR evaluation. The other thing that's used in IR evaluation, and that should say IR, not IM, is that you can look at what's called the fingerprint of a molecule. Molecules with several bonds do have different vibrations. So looking from 400 to 1400, that's going to be pretty consistent and can be used to make a fingerprint or a sample spectra and stored in a database for specific molecules. So heroin is one that has a fingerprint stored, and the blue down here is the fingerprint. Here's the fingerprint for heroin, and if you match from roughly 400 to 1400 with the unknown sample above in black, they're virtually identical. So it would seem likely that even though there's not quite as tight a match, but still a very good match in the rest of the spectra, this molecule seems to be heroin. So when you have a spectra, you go through and try and identify each trough and come up with a possibility for the molecule. So if I look at this molecule, I'm going to start to the left here, and I see that there's a couple of troughs here just above and just below 3000. So 32 to 36 could be an OH bond in an alcohol, but I'm not quite as high as 32. It seems more likely I've got some CH bonds belonging to an alkane, alkene, or arene. Just below the 3000, it would appear that I have an OH bond in a carboxylic acid. Now, if I have an OH bond in a carboxylic acid, I should also have the CO bond in the carboxylic acid, which is up here, which means I should have a peak around 1700, and I do have a very strong peak around 1700. So far, I think I have some CH bonds. I think I have the OH bond in a carboxylic acid, and I think I have the CO bond. So those are the 3 I've identified so far. Then I have this peak around 1500, which might be a fluoryl alkane. It could be a CO in an alcohol, ester, or ether, although I'm pretty sure I have a carboxylic acid. Or it could be the C double bond in an alkene, which it's a little high for. So I'm really not sure what to make of that particular bond. Around the 1200 or so, again, I don't see anything jumping out at me. A fluoryl alkane, perhaps. Although I also have peaks over here around 600 and 800, which would lead me to believe it's a chloryl alkane. So at this point, I'm pretty confident that I have at least ethanoic acid with the possibility of some kind of halogen attached to it, fluorine or chlorine. But at this point, I'd probably want to look at a fingerprint of my expected or suspected molecule and see if I can get a better match for these unknown troughs. Now, that's a little bit difficult and a little ambitious and more will expect you to do. the more likely question you'll get from IB is to locate the identifying characteristics on the spectra for ethanol below. Well, first I need to know what ethanol looks like. It's got 2 carbons and an alcohol, or a hydroxyl functional group. That means it also has 5 hydrogens single bonded to the carbon. So I've got a couple things to look for. I've got the OH in the alcohol group, which is supposed to resonate up here at 3300 to 3500. So I seem to have that covered right there. That seems to be a trough for my hydroxyl group. My CH should be resonating around this particular region here. Sorry about that. So in here, that appears to be my CH groups. And I don't have resonance for this carbon-carbon single bond. So back here in my fingerprint region, again, I could actually do a fingerprint comparison to ethanol, but as far as identifying characteristics for my list here, I just have the hydroxyl and the single bond between the carbon and hydrogen to call out.